Here's sort of a bad picture of our PQ, QR, RS, and SP vectors. Just for reference, we're not actually using the picture, but we want to see in context where these things are. And what we're actually going to do is we're going to figure out the equation that has to be satisfied by a point XYZ that lies on the plane that you would get by laying your envelope or laying something flat across the RS and SP vectors. Okay, so we hypothesize, first of all, we haven't given coordinates to these points. So we're going to suppose that S is the point 4, -3, 15. The 15 matches the 15K up to the point S. And the 4, -3 could be anything because we didn't actually assign values to those points down in the plane. Okay, we didn't assign coordinates because we didn't need them. All we needed was the vertical vectors to get these vectors and do everything we've done so far. So we're going to let U be the vector x, y, z, and we've got this red vector here that, just as on the preceding video, stands for the unit vector in the direction perpendicular to RS and SP, which is therefore perpendicular to every point in the plane defined by RS and SP. Now that perpendicularity is going to be the defining characteristic that allows us to determine the equation of the plane as follows. Okay, let U be some point x, y, z out here in space, anywhere. Okay, so U's out there someplace smiling at us. Then the vector SU, you get the coordinates of this vector just by subtracting the coordinates of S from the coordinates of U, because your initial point is S, your middle point is U, and you should totally understand that. The first thing we did in this course was do a vector PQ, okay, where we subtracted the coordinates of the point Q from the coordinates of the point P. If you didn't get that, you need to review it, because we've been using that every day since we started in the 4 classes we've had. Okay, so here's the vector SU, x minus 4, y minus -3, and z minus 15. There it is. Okay, now here's the big deal. U is in this plane if this vector SU is perpendicular to this unit vector. That's it, and that's pretty intuitive. We'll probably talk about it a little more next time. If that isn't kind of obvious to you, think about it, and we'll probably talk about it a little more in the future. Okay, so here's a big deal. I've made the statement. Using the plane of RS and SP passing through the point call that point U, and that point is S. And I don't know what I had there before, but I already made a mistake in labeling this point. S is the point 4, -3, 15. Okay, if and only if the vector SU is perpendicular to that unit vector that we calculated earlier. The 0.8i plus 0.6i plus 0.8j minus 0.4k, I think. That's plus 0.4k. Yeah, that's all plus. Everything's out into the first octant. Okay, now it doesn't have to be the unit vector. It could be the original RS cross SP vector, which I haven't drawn, but it comes out and it's much longer. You know, PQ is a little over 5 units long, and the RS cross XP is 40 units long, so I don't have room to draw it. It's convenient to use the unit vector, at least in the picture. But I could equally well say, well, this SU vector is perpendicular to this unit vector, if and only if it's perpendicular to the original vector we used to get the unit vector, because the unit vector is just a multiple of that original RS cross SP vector that we know has to be perpendicular to the RS and SP vectors. Okay? So, there's the condition. SU, this vector x minus 4, y minus -3, z minus 15, has to be perpendicular to any vector that's perpendicular to the plane. Okay, so the plane consists of all the points such that the vector from S to the point is perpendicular to the vector that's perpendicular to the plane. And if you think about it, that's exactly the way it ought to be. Okay, well, then we do that. We say that SU dotted with the unit vector has to be 0, because that's our test for perpendicularity by the dot product. Okay, so SU perpendicular to unit vector if and only if SU dotted with the unit vector is 0. So that SU, now I didn't do SU dotted with the unit vector. I went ahead and did SU dotted with RS cross SP because I wanted to use those numbers. Okay, SU dot RS cross SP. There's our SU vector. There's our SP vector. There's our SU vector. There's our SU cross SP, RS cross SP vector. And I could have used the unit vector here. And I just do that dot product, which is very easy. X minus 4 times 25, Y plus 3 times 32, Z minus 15 times 20. There it is, equal to 0. And I get this equation. So now we have an equation of the plane in that a point is in the plane if its x, y, z coordinates satisfy this equation. Now I assume I did the arithmetic right to get that negative 104. Just look at it again, I think it's right. Okay, so if I have an x, y, and z that makes this true, like for example, x equals negative 104, y equals 0, z equals 0, well sorry, no, 25x equals negative 104, so x is 104 divided by 25, which is negative 1.16. So negative 1.1600. Maybe that makes sense in terms of the orientation of this figure. Maybe it doesn't. You want to think about that. And if you want to specify the values of x and y, you can always find a z. It gives you a point. So there are a lot of neat things about the equation of a plane that allows us to do a lot of really important vector calculus. Okay, so anyhow, here's the equation of plane through point S. I could, and I'll do it real quick up here. I could have done SU cross the unit vector, but I can only approximate that because I only approximated the unit vector. So that would be x minus 4, y plus 3, z minus 15, dotted with 6i plus 8j plus 4k, 0.6i, 0.8j, 0.4k, which is close to being a unit vector. I think if you calculate the accurate coordinates, they'll come up, there's a very good chance they'll round off to the numbers I have here. But it's a round off and there's some error because, as you can check, the magnitude of this vector is about 1.08, I believe. It's not 1. 0.6i plus 0.8j without the 0.4k would have a magnitude of 1. Okay, well, anyhow, that's a digression. Now, what we're doing is we're doing dot product of this vector with this vector. And, you know, this is the I component. You multiply the I component by the I component. You get 0.6 times x minus 4 plus 0.8 times y plus 3 plus 0.4 times z minus 15 equals 0. And then I'm going to multiply all these numbers by 10, meaning I'm just going to, that'll just remove the decimal in front of them, and I'll get 8x, 6x. Easier to make the x into a y. Okay, plus 8y plus 4z equals negative 24 and coincidentally 24. So get negative 60. And that's not going to be consistent at all, but that's okay. Okay, so there's one equation of the plane. And negative 60 doesn't match up well with this. These numbers here are about 4 times these numbers. This number is a lot less than 4 times this number, which means it's possible I made a mistake there. But I don't see it. I don't see it. Well, you can check my arithmetic. Just illustrating, though, that I could have used the unit vector. I used the actual RS cross SP because it was more accurate than my estimated unit vector. Okay. Yeah, I'm still not seeing it. Okay, so there it is. And that should give you a pretty good background for the things that you're going to be asked to do in the next couple of assignments.